To learn quantum programming, it is essential to understand quantum mechanics principles and how they differ from classical paradigms. Quantum programming involves manipulating qubits, which can exist in multiple states simultaneously, unlike bits in classical computing. Key concepts include superposition and entanglement, which allow quantum algorithms to solve complex problems more efficiently than classical ones. Quantum programming represents a new paradigm in computing, leveraging quantum mechanics principles to perform calculations beyond classical capabilities. Unlike classical programming, quantum programming requires a deep understanding of superposition and entanglement, which empower quantum systems to process massive datasets. Essential skills include linear algebra, probability theory, and familiarity with classical programming languages like Python. Quantum programming is essential because it harnesses quantum phenomena to tackle complex problems intractable by classical computers. Such programming excels in cases like cryptography and optimization, where classical methods falter. It provides significant speedups for specific tasks, potentially revolutionizing fields like materials science and pharmaceuticals. Classical programming processes information through bits, which are either 0 or 1, whereas quantum programming uses qubits that can represent 0, 1, or both simultaneously. This ability, known as superposition, allows quantum computers to perform many calculations at once. Additionally, entanglement and measurement-based computations enable new computational strategies not feasible with classical systems. To begin quantum programming, a strong foundation in linear algebra and probability theory is crucial, as these are fundamental to understanding quantum mechanics. Familiarity with a classical programming language such as Python is also beneficial, as many quantum computing libraries are based on it. A basic understanding of quantum physics concepts will aid in grasping the unique properties of quantum computers. Quantum computing models include the circuit model, where computations are performed using quantum gates arranged in a sequence to manipulate qubits. Measurement-based quantum computing uses a highly entangled initial state, and computations occur through measurements, offering a different approach to quantum algorithms. Topological quantum computing leverages anyons that perform computations based on their braiding, providing robustness against errors due to their topological nature. The current quantum computing landscape features real quantum processors, such as those developed by IBM and Google, which can be accessed for research and development. Simulators like Qiskit and Cirq are crucial for prototyping quantum algorithms without needing physical quantum hardware. Additionally, platforms such as IBM Quantum Experience and Amazon Breakit offer cloud-based quantum computing services, enabling broader access to quantum technologies. In quantum programming, understanding the fundamental concepts like qubits, quantum gates, and circuits is crucial, as these form the building blocks of quantum algorithms. Qubits are the quantum version of classical bits and can exist in superposition, allowing them to represent multiple states simultaneously. Quantum gates, such as the Hadamard and CNOT, manipulate qubits to perform computations, analogous to logical gates in classical computers. Qubits, the basic unit of quantum information, can be mathematically represented using state vectors in a two-dimensional complex vector space. The concept of superposition allows qubits to exist in a combination of the 0 and 1 states, which is visualized using the block sphere representation. This visualization helps in understanding the quantum state's rotations and transformations during computations. Quantum gates are fundamental operations that affect qubits, such as the Pauli gates, Hadamard, CNOT, and Toffoli gates, each with distinct matrix representations. The polygates, X, Y, Z, alter qubit states through rotations, while the Hadamard gate creates superpositions. The CNOT gate is crucial for entanglement, and the Toffoli gate, a universal gate for quantum computations, manipulates 3 qubits for more complex operations. In quantum measurement, observing a qubit collapses its superposition state into a definite state of either 0 or 1. This collapse is a critical aspect of quantum program execution, as it can affect subsequent quantum operations and outcomes. For example, measuring a qubit in a superposition of states during an algorithm execution changes the probability distribution and alters the program's results. Quantum circuits consist of quantum gates arranged sequentially to perform calculations on qubits, similar to how classical circuits use logic gates. These circuits are structured using gate sequences that manipulate qubits' quantum states, often influenced by classical control to adjust quantum operations dynamically. For instance, a circuit might use conditional operations where classical bits dictate the application of specific quantum gates. Quantum computing systems are inherently subject to noise and errors, which arise from environmental interactions and imperfect control. To mitigate these issues, error correction techniques such as quantum error correction codes and fault-tolerant designs are employed to maintain computational integrity. An example of such a technique is the Shor code, which protects against qubit errors by encoding logical qubits into entangled states. Setting up a quantum programming environment involves installing quantum software development kits, SDKs, like Qiskit or Cirq, and leveraging resources from cloud-based platforms like IBM Quantum Experience. These tools enable developers to simulate quantum circuits and execute programs on real quantum processors accessible via the cloud. It's vital to engage in debugging and optimization practices to enhance program efficiency and accuracy. Selecting a quantum programming framework requires understanding the strengths of options like Qiskit, Cirq, and QTP, each tailored for specific use cases. Qiskit, for example, is ideal for IBM's quantum processors and emphasizes a modular approach, while Cirq is often used for Google's Sycamore processor and supports advanced quantum algorithm development. QTP, on the other hand, excels in quantum dynamic simulations, making it suitable for research-focused applications. To install Qiskit, first ensure Python is installed, then run pip install Qiskit to download the SDK. Set up your development environment by configuring an integrated development environment like Jupyter Notebook, which is recommended for writing and testing quantum programs. Verify the installation by importing Qiskit in a Python script and running a simple quantum circuit simulation. Running quantum programs on classical simulators like the Qiskit Air simulator is crucial before deploying on real hardware. This involves writing your quantum code and executing it using air_backend, chasm_simulator, which mimics quantum processing without the noise present in physical quantum computers. Such simulators allow for debugging and optimization in a controlled environment, ensuring code correctness. To access cloud quantum computers, first create an account with a provider like IBM Quantum or AWS Breakit. Use the provider's interface to submit quantum jobs, often via an API or SDK that allows remote execution on quantum hardware. This setup provides access to powerful quantum processors from anywhere, facilitating experimentation with cutting-edge quantum technologies. Debugging quantum programs involves using tools like Qiskit Ignis for error mitigation and understanding error sources. Optimization techniques include reducing circuit depth and using efficient gate sequences to minimize noise impacts. Profiling tools such as Qiskit's transpiler help analyze and improve circuit performance by converting high-level descriptions into optimized quantum operations. Your first quantum program could involve creating a quantum circuit using Qiskit, starting with initializing qubits and applying gates like Hadamard. Run the circuit on a simulator to observe superposition effects and measure results, which collapse the quantum state to classical bits. Analyze and interpret these results by comparing expected probabilities with observed frequencies to understand quantum behavior. To construct a basic quantum circuit with a single qubit, start by initializing the qubit in the state 0. Apply quantum gates such as the poly-X gate, which flips the qubit state, or the Hadamard gate, which creates a superposition. These gates are represented by specific matrices that transform the qubit state accordingly, enabling basic quantum operations. The Hadamard gate is used to create superposition by transforming a qubit from the state 0 to an equal probability of being 0 or 1. By adding a measurement operation after the Hadamard gate, one can observe the probabilistic nature of quantum states, typically yielding a 50% chance for each outcome. This experiment illustrates the counterintuitive principles of quantum mechanics, essential for understanding quantum algorithms. To create a Bell state, begin by preparing 2 qubits in the state 0, 0, and then apply a Hadamard gate to the first qubit. Follow this with a CNOT gate, using the first qubit as the control, which entangles the qubits, resulting in the state 0, 0 plus 11/2. Measuring these qubits will show correlated results that exemplify quantum entanglement, a key resource in quantum communication. The Deutsch-Jozsa algorithm is a simple quantum algorithm that determines whether a given function is constant or balanced using a quantum circuit. Implement this algorithm by preparing a superposition of input states and applying a series of quantum gates to transform these states. This process requires only a single evaluation of the function, demonstrating the quantum speedup over classical methods. To interpret results from a quantum program, analyze the measurement outcomes, which are usually binary strings representing qubit states. Compare these results against the expected probability distribution predicted by the quantum algorithm. This analysis helps extract meaningful insights, such as verifying the success of an algorithm or diagnosing errors in quantum state manipulation. Key quantum algorithms like Grover's and Shor's algorithms are essential in quantum programming, each offering unique efficiencies and breakthroughs. Grover's algorithm provides a quadratic speedup in unsorted database searches, while Shor's algorithm revolutionizes number factoring, posing potential threats to classical encryption. Implementing these algorithms requires familiarity with quantum programming frameworks such as Qiskit or Cirq, which provide the tools needed to manipulate qubits effectively. Quantum speedup is achieved through quantum parallelism, enabling certain algorithms to process information exponentially faster than classical counterparts. For example, Shor's algorithm can factor large numbers in polynomial time, a task that is infeasible for classical computers. This speedup is not universal for all problems, but applies to specific computational tasks where quantum states can be exploited. Grover's algorithm is designed to search unsorted databases with a quadratic speedup, reducing the number of operations from O(n) to O(n). The algorithm utilizes quantum superposition and the oracle function to identify the correct solution efficiently. To implement Grover's algorithm, one must initialize qubits, apply the Grover operator iteratively, and measure the output to obtain the desired result. Shor's algorithm transforms the field of cryptography by enabling the efficient factoring of large integers, which is foundational for RSA encryption.